Hi, everyone. Welcome to the July Sci-Cafe. We'll get started in just a couple of minutes. Okay. Welcome, everyone. Tracy with us. And the topic of today is investigating the hydrologic alteration as a driver of shifting forest species composition in the Apalachicola River floodplain. And we're excited to have him here. He currently is a professor at Louisiana State University. He has spent the last 4 years investigating the trees around the Apalachicola River and how they responded to changes in flood patterns and how they regenerative strategies explain observed changes in forest types, which have ecological implications within the flood plain and downstream. John is a member of a multidisciplinary team organized by the Apalachicola Riverkeeper to restore floodplain connectivity around the Apalachicola River. He received his PhD in ecological restoration from the University of Florida in August and now works as a research associate at Louisiana State University. John, take it away. Oh, we'll have time for questions later. You can type them in the questions box. I've also unmuted everybody, so at the end you can unmute yourself and ask a question.
Awesome. Thank you. Yes, please let me know if you can hear me all right. Grateful to be here today. Thank you for the invitation. It's exciting to get to share my PhD dissertation work. This is kind of a repeat of my dissertation defense, but a little more casual. I'm wearing my UF shirt today to represent, but I am currently employed at Louisiana State University, but still trying to focus on the Apalachicola as well with my current work as well. All of this work was funded through a grant from the National Fish and Wildlife Foundation that was received by the Apalachicola Riverkeeper and offered to us at the University of Florida. And so I'm very grateful for the opportunity to be a graduate student in that project. You'll see in this first picture here some pictures of some floodplain tree species seedlings. It's kind of the focus of what we'll be talking about today. A lot of my work involved looking at the youngest life stage of these species, which is when they're most vulnerable to stressors like moisture deficits, a drought, too much moisture, so flood, extreme heat, predation, things like that. And so I wanted to understand those dynamics a little bit better and see if that could help us understand why we're seeing changes in forest species composition within the Apalachicola. So moving along, I always like to start out with some pictures of all the people that have helped me. There's too many to name and to take pictures of, but this is just a few of them just to explain, a lot of work went into this and a lot of hands were involved to help me achieve these experiments and these final results that I have. So I'm very grateful for all those people who helped out over the years. And that's Jay Sharman in the top left there, standing with me there, who brought me on and helped me out very much through my career. So our agenda today, we're going to get some background about bottomlands and floodplain forest species composition, generally throughout the Southeast, and then we'll focus more on the Apalachicola and its current problems. Then we'll break down the other chapters of my dissertation in chapters 2 through 4, which are 3 different seedling experiments I did. One focused on their response to drought, one focused on their response to flood, and then one where I really focused in on their youngest stage, starting from seed, to see how they responded to different stressors. And then we'll talk about how we can apply all those results at the end. So let's start with chapter 1. We'll talk about floodplain connectivity and the Apalachicola River. So floodplains are the low elevation areas, often called bottomlands, that are adjacent to rivers and streams. They catch the spillover from seasonal flows that breach the main stem banks. Floodplains did not have to be large like what's depicted here as a large river floodplain. Even small streams can have their own small floodplains next to them that are not very wide, but still play an important role in, say, flood mitigation or the processing of water and pollutants and nutrients that might be in that water. They still play a very important role, whether these are large or small floodplains that we're talking about. And so within floodplains is a heterogeneous or variable landscape created by seasonal floods, erosion, and sedimentation. And with this landscape comes an elevational and hydrologic gradient along which various vegetation species mixes are adapted to exist. I have 3 described here as high bottomland hardwood, or high bottomland, low bottomland, and swamp habitats. Generally, your high elevation bottomland sites often exist next to the main stem of the river or stream, where sandier, coarser, heavier soils exist. So this is where the heavier, coarse sands drop out of the water column during floods when they come into contact with vegetation and water slows. And so that's why you get those higher ridges next to the main stems of streams. Where floodplains then widen and elevation declines away from the main stems, you get your low bottomland sites with more loamy or clay silt alluvial soils. So these are less heavy sediments that then drop out. And eventually we get make our way down to the lowest elevation areas that we call swamps, where they are poorly drained, heavy clay soils, very dense, that dominate there. And the vegetation in those areas are adapted to frequent and long duration flooding. So in several major southeastern US floodplains, seasonal high flows can typically last from December to early May due to rains from passing storms and fronts or spring snowmelt in northern drainage basins. So a hydrologically connected floodplain and its heterogeneous habitats provide a significant source of fresh water, dissolved oxygen, nutrients, and detritus to the bay estuaries, where fisheries that support local economies rely on that fine balance of these inputs. Now in the southeastern US, we have done a great job of disconnecting floodplains through either the construction of levees that allow expansion of communities and agriculture in these fertile soils. We have also altered flow regimes through construction of dams for storage and water storage and hydropower that help maintain agriculture and drinking water for our communities. This has created a drying trend within southeastern floodplains and caused changes in forest species composition that affect the ecosystem services provided by these habitats. In some systems like the Apalachicola, it is believed to have created an imbalance in these inputs to bay estuaries where fisheries are currently in decline, as many as you may know, the oyster fishery that has had a moratorium for the past several years. So let's focus on the Apalachicola now. It is the largest river by water volume in the state of Florida. It's not the longest river, but is the largest in terms of the amount of water that flows through it. And also it is the largest forested floodplain around that river in the state of Florida. It's a significant contributor of fresh water and nutrients to the eastern Gulf of Mexico, the largest being the Mississippi River to the west there in Louisiana and Mississippi. So the Apalachicola is at the southern end of the Apalachicola Chattahoochee Flint River Basin. So this large area that collects all the rainwater and snow melt that eventually works its way down to the Gulf. The Apalachicola is on the lower end of that. And so being on the lower end, you're at risk of whatever water extraction or alteration in flow happens upstream in the other rivers that go up into Alabama and Georgia. As far as upstream influences on the flows that eventually make it to the Apalachicola, there are 5 major dams or reservoirs on the Chattahoochee, which is depicted in red here. And the jars kind of show how much storage each one of those dam reservoirs has. The largest being Lake Lanier up near Metro Atlanta, which supplies the majority of the drinking water for the ever-expanding Metro Atlanta area. So as you can imagine, there's a lot of demand coming from that reservoir. Now there's also a lot of water that gets extracted for irrigation, such as in Southwest Georgia, where center pivot irrigation has expanded since the 1950s, and it's a very it involves heavy extractions of water throughout the more karst river system that is the Flint River. So not as wide of a floodplain on this river. There's a lot of bedrock that it flows through, and so it's fed more by groundwater. But that also influences inputs of water down into the Apalachicola when all the wells that feed the irrigation for agriculture pull out of that system. And so this tends to exacerbate drought events. And so more water gets pulled or more water gets stored during drought events to provide for municipalities or agriculture. And that leaves the Apalachicola on the losing end of that battle, which has led to multiple legal battles over the years over water apportionment between these 3 states. So we have that problem with water use upstream, but we also have within stream issues as well. We've had issues with channel degradation, such as when the Jim Woodruff Dam was complete. We had issues with channel incision and channel widening from dredging projects that happened within the system. So basically, in the pre-dam era, if you look at rates of flow in the pre-dam era and the post-dam era, you could look at the same rate of flow, but in the post-dam era, that same rate of flow results in a lower level of the river. So it's widened and it requires more flow to get more water and higher levels of water that eventually flood into the floodplain in the post-dam era. So some pretty significant issues we're dealing with there. In terms of dredging, the main problem we had was that when the Army Corps went in and dredged for navigation, they took the sand and spoils and they put it on the banks of the river rather than removing it from the system completely. And so the problem here was that during seasonal floods, it would come and suspend all these sediments, which would then make its way downstream and out into the floodplain and plug up natural sloughs that would feed water out into the swamps in the bottomland areas where these critical habitats rely on seasonal flood pulses. And so in this middle picture here, you see a sand plug at the head of what's called Spider's Cut down in the lower middle reach of the river. And the bottom picture is even more of that coarse, heavy sand out almost a mile out into Spider's Cut. And we believe that this source of this sand is from these dredged deposits from years prior. So now part of our restoration activity is to go and remove these sand plugs and the sand within these sloughs, Douglas Slough, Spider's Cut, and then there's another restoration area further south. We want to see if we can restore the connectivity within this system, which we think will help maintain these habitats and especially the forest types within. So we have to understand first, if we're focusing on the forest types, how hydrology affects species distributions in a floodplain. And generally, forest species get lumped all into they're just bottomland hardwood species. They're all water-loving species. They prefer flooding. But really, there are minute differences between these groups of species and the elevations and where they can exist along the elevational gradient within a floodplain. So a difference of 1 to 3 feet can make a big difference on what species you see literally within 15 feet of each other. So yes, as the river water comes up and down, like you see this bar moving here, that's going to dictate the frequency and the timing of flooding within all these habitats and the type of species that are adapted to those types of conditions. So on the higher elevations, the fronts, the high flats, and the ridges, this is where you're going to have your coarse, more well-drained soils, the sandier soils. You have species like elm, sycamore, pecan and sugarberry, oak species like nuttall, green ash, red maple that prefer some of these sites that don't have as frequent and long duration flooding. As you move down in elevation, you get your low bottomland hardwoods, your overcup oaks, your water hickories, and your low flats here and sloughs that prefer a little bit longer duration flooding and frequency of flooding, or at least they can handle it, and that's what allows them to dominate in these areas. And then down in the lowest elevations is where we reach the swamp, and we have the species that are adapted to the most frequent and longest duration flooding. And so that's where we find our water tupelos and our bald cypress tree species. So within the Apalachicola specifically, we have observed that the low bottomland hardwood species, your overcup oak and water hickory, have been encroaching into the swamp habitats and reducing, we believe that's impacting the reduction in density of bald cypress, not bald cypress, but specifically water tupelo, your swamp species. And this is all, we believe, a result of the drawing effect that water demand upstream and within stream degradation, channel degradation, has resulted in this dynamic here. So the first group of people to study this were some USGS scientists. On the top right there, you have Helen Light, and on the bottom, you have Melanie Darst. Helen Light did some of her master's work in the Apalachicola River floodplain, and they both worked, Helen eventually worked with Melanie Darst with the USGS, where they studied forest dynamics within this system in response to all of the alterations in flow since the 50s. And what they observed when they monitored the forest in the 1970s through 2004 was a reduction in floodplain forest trees, just a general density, a reduction in density of all trees within the floodplain in the areas that they monitored. They also noticed that swamp tree species, so down at the lowest elevations, their density had decreased by 37%, which is a pretty significant reduction and slightly alarming. Within that group, they found that water tupelo, its density had decreased by 20% in their monitoring plots. They found that Ogeechee tupelo, a species that it's very important to the tupelo honey trade in the area, its density had decreased by 44%. And popash, its density had decreased also by 38% within their plots during that time period. So clearly a significant reduction in these species that prefer longer duration and frequent flooding. And so you might be asking, why are we concerned about this? Well, these species, other studies have observed that these species, through their litter fall, contribute a significant amount of nutrients to the system at a faster rate than some of the other species that prefer drier environments. And in general, in a drier environment, they have found that a decay of all litter fall is much slower. And so there have been some studies that have linked isotopes of nutrients in the bay to forest species in the floodplain. And so primary productivity in the floodplain itself has been linked to secondary productivity down in the Apalachicola Bay. And so that's why we're concerned about this change in species composition here. Think about it this way. Do you get the same level of nutrition from eating a spinach leaf as you do from eating a piece of, let's see, I'm trying to think of a different type of lettuce that has less nutrients? No, it's not the same nutrition of saying iceberg lettuce to a leaf of spinach. The same type of scenario plays in here with the different tree species and the leaves that they contribute to the system through litter fall each season. So using satellite imagery, I've also been able to monitor this change in forest species composition. Basically, we can measure through satellites the reflectance of the sun's rays. Okay, so when the sun, its radiation comes down in the forms of photons of light, it then gets reflected or absorbed at different rates by different species. And so our sensors on satellites can determine what that value is of reflectance from those certain species, and then allows us to identify them down on the ground. And so using that technique and truthing or proving where those forest species composition mixes are, we can then create these maps to see how things have changed over time. And so you can see how that area purple, which represents the swamp species, has become more saturated with green and gray. Gray is the high bottomland hardwoods that have begun to encroach down into the swamp. And then the green also means there's mixes of the bottomland hardwoods that are now starting to take over in the swamp area. So this was a way for us to kind of prove what Helen and Melanie were saying about the species composition shifting within this area. So this is where I come in with my PhD work, where I wanted to answer the question, what is driving these species shifts? Is it increased hydrologic variability? If we look at the typical low flow year in the period before the dam, we notice that in the lowest 10% of swamps within the floodplain, the time period that the water drops out of the system is 78 days. So this is the time period that a tree species would have for its seed to sprout and to put on enough growth to achieve a level of resilience that would allow them to survive future stressors, whether that's a flood pulse like you see in these blue pulses here later in the summer, or winter flooding later on during December, January, and February. So that time period was 78 days for them to sprout and grow and get that level of resilience. Now in the post-dam era, that time period has greatly expanded down in the lowest 10% of swamps. And so we have to wonder whether these swamp species that are used to frequent and long duration flooding, are they struggling to survive in this now much drier environment? So we asked the question, can swamp species not advance in a drier floodplain? Looking at the literature, we've noticed improved growth of water tupelo seedlings in flooded soils rather than drained soils. So that kind of shows us, okay, they do grow best in flooded soils based on this observation. 19% mortality of Ogeechee tupelo was also observed after 63 days of drought, so no added water. Water tupelo did not see any mortality during that time period, but its metabolism was reduced, so it was showing some stress. 1-year-old oak seedlings, on the other hand, your low bottomland hardwood species, they were minimally affected by drought in another study in 1989. So this brings me to my first experiment, which was investigating thresholds for drought resistance in floodplain forest tree seedlings. And this paper was published just yesterday, so I'm very excited to announce that. The experiment we did from December through May in a controlled environment, so in a greenhouse where we were simulating growing season conditions. And we were using 7-month-old seedlings from an experiment that we'll talk about later on that started from seed. So they had experienced one growing season. They were only 7 months old, but they had enough time to put on a decent amount of growth. And we tested the 3 swamp species that were in decline, water tupelo, Ogeechee tupelo, and pop ash, and then their 2 common competitors in the Apalachicola, which is water hickory and overcup oak. We wanted to see if increasing drought simulation after initial soil saturation, how that would affect mortality, and then what soil moisture would cause mortality. So our questions were, does drought stress cause faster mortality of swamp species than their competing low bottomland hardwood species? And our hypothesis was that the time to reach almost 100% mortality would be shorter for swamp species than low bottomland hardwood species. We also wondered, what thresholds of soil moisture cause mortality of these species, and do they differ? And our hypothesis was that soil moisture mortality thresholds would be greater for swamp species. So swamp species would experience mortality at a higher level of moisture than low bottomland hardwood species that would be a little bit more tolerant of lower soil moisture, so a drier soil. So in testing this, we observed here, as you see on the figure on the right, that there were very little differences, minimal differences between all of these species. So as the weeks went on and the soil got drier and drier and mortality started to occur, the rate of mortality was pretty much the same between all these species. In terms of the threshold for when mortality began, there was also little differences between these species as well. So our conclusions from this study were that the rate of mortality does not differ between 7th-month-old swamp and low bottomland hardwood species. The moisture mortality thresholds are also similar. And so floodplain soils must become extremely dry to kill 7-month-old seedlings of these species. If you noticed on that last figure, mortality didn't occur until after 5% soil moisture. It took almost 18 weeks of no water added. So imagine going 18 weeks without any rain in this system. That's what it would take to cause mortality of these seedlings and to have a unsuccessful regeneration year for these species. The likelihood of that happening often enough is very slim. So that tells me that drought, that level of drought is unlikely a factor determining success or differences in success and competition between these species within this system. Remember that they don't have to have a successful regeneration year every year. It only has to happen every so often. And so this shows that this type of event, drought event, is unlikely to occur often enough to cause differences in competition between these two groups. But these were 7-month-old seedlings. So these tolerances may differ at an earlier life stage, which means we need more study of that. So going back to the drawing board and asking, can swamp species not advance in a drier floodplain? It does not show me that the extended drought period is necessarily what's driving their lack of success and their decrease in density. So I had to ask, what was it that originally did not allow low bottomland hardwood species to exist in the swamps, in the lowest elevations? Can they not advance in these flooded swamps? Is it those flood pulses that you see later in the summer that keep out low bottomland competitors? Or is it the higher winter floods, that duration that keeps them out of the lowest elevation swamps? If you look, we've lost those pulses in the late summer in the post-dam era, so in the red here. And there's a lot of variability in the winter flood dynamics now. So I have to wonder, was it those, in the pre-dam era, was it the length of time or those flood pulses that could keep low bottomland hardwoods from surviving? If we look at the literature, it shows that some species can pause their metabolism during dormant season submergence, so during winter flooding, which boosts their survival when the spring season comes around. Overcup oak seedlings, a low bottomland hardwood, survive 17 weeks of flooding through dormant season and growing season flooding, but that was not submergence. So it was not water over the terminal bud. That was just flooding that either saturated the soil or a little ways up the stem. There's a big difference between flooding just a little way up the stem versus covering that top terminal bud of the seedling. On the other hand, 60% mortality of overcup oak seedlings occurred after dormant season submergence in a field study. So this is where they were completely inundated and you saw more stress and more mortality. There was 80% survival of 9-week-old overcup seedlings after 25 days of submergence, so complete inundation, and only 50% survival of 6-week-old seedlings. So that shows a difference in survival dynamics between different ages of seedlings. On the other hand, 87% survival of 1-year-old water tupelo seedlings was observed after February through July submergence, though their productivity was reduced. So this brings us to chapter 3, my second experiment. I wanted to evaluate dormant season flood duration as an indicator of seedling survival between these species. So if we look at this time lapse on the right, this is from the low end of Spider's Cut down in the back swamps where Tupelos dominate the overstory. And it gives you an idea of the dynamics of flooding. This is the winter season, eventually moving into the spring. And so you see how high and frequent and long duration flooding exists until you reach the spring, where you see all the green and emergence start to happen with some of the ground vegetation. And then eventually we'll make our way into December and January, where floodwaters again return in the winter season. And so you have a pretty significant amount of time during that winter season that you have overtopping of seedlings down in those bottom swamps. And so you wonder, is that what does not allow the low bottomland hardwoods to dominate there? So our experiment was, we took a pool, as your typical Intex pool from Walmart, was what I could afford at the time. And I took some residual seedlings from my other experiment. Again, they were 7 months old. And I tested them from January through June. So this is kind of a typical winter flood season going into the spring and summer months. Sometimes it can vary how long that flooding occurs each year, how long high waters in the swamps last into the summer. So I wanted to test a pretty long amount of time to see if there were any differences. I did this in an open environment at UF Milton, so it was going to get typical winter season temperatures. I tested the same 5 species, the 3 swamp species that were in decline, and then the 2 low bottomland hardwood competitors, which are water hickory and overcup, 7-month-old seedlings. I tested increasing submergence. So I tested a group for 1 month, and then I took them out, and then 2 months, 3 months, and 4 months to see if there were any differences. I looked for post-submergence mortality and the rate of flushing individuals. My questions were, does increased duration of dormant season submergence reduce survival? And I believe that survival will be reduced across the board for all species with increased duration of flooding. Does survival and productivity of swamp versus low bottomland hardwood species differ with increased duration? And I believe that the low bottomland hardwoods would have survival and productivity would be less than swamp species with increased duration. So let's look at the results. It's very simple. All I have to do is throw up a table here because there were no significant differences within any species, within any treatment. There was almost 100% survival across the board. They survived anything between 1 and 4 months of flooding, which was not what I expected at all. So no effect on survival and productivity. If the other thing I measured was the rate of leaf flushing between all these species to see if there were any at least signs of stress if they didn't die. You'll notice after 1 and 2 months of flood, there seems to be some differences there, but that was because this was during the winter months still, and certain species come out of dormant season a little bit slower than the others. So water hickory and pink there and overcup were a little bit slower to come out of dormant season. But if you look at 3-month and 4-month flood, which is in the warmer temperatures of the spring, you see that there's very much similarity in leaf flushing between all the species. So no differences in stress at all between these species. So the conclusion here is that level of flooding with 7-month-old seedlings that have reached that level of resilience, they're pretty darn resilient to long duration flooding, even into the summer months there. So with that, that brings us to our much larger study, where I wanted to focus more on what's going on at the earliest life stage. I'm not getting much response once they've had a full growing season. So I need to know what's happening when they're at their most delicate stage, starting from seed. And does that explain where we're having successes and failures with these species in the floodplain? So this chapter was entitled Flood Dynamics and Tree Resilience, First-Year Seedlings of 5 Floodplain Forest Species Responding to Diverse Inundation Scenarios. So this experiment, we did 1 typical growing season in the Apalachicola, May 10th to November 10th. May 10th is typically when floodwaters come down in the Apalachicola within most of the swamps. And then toward November 10th is when, you know, the growing season is pretty much ended and you're getting ready for the oncoming winter floods. This was a full sun environment At UF Milton, this was not inside a greenhouse, so it was an open environment. The species we tested were the same 5, the swamp species and the 2 bottomland competitors. We collected most of these seeds from the floodplain itself, so they were adapted to that floodplain's current hydrology. We ended up planting 7,500 individual seeds within individual bags. It was a lot of work. We tested 12 different moisture regimes that might be experienced in the Apalachicola. And what we measured was emergence. So when they germinated and came up from the soil, that rate of emergence to see if there was any difference in stress related to the rate. Mortality, did they recover from stress? And then I wanted to know their final height. So are there differences in who attained the highest height that might have the best advantage in surviving winter floods? Our treatment groups were different durations of either ambient conditions. So since it was an open environment, I couldn't control for rain or precipitation. So whatever fell in the form of precipitation was the only water that was added in ambient treatments. In saturated treatments, they received rain, but also water was maintained about halfway up the soil column. And then in the flood treatment, I couldn't do complete inundation for seedlings that had already sprouted, but I was able to get a good ways up the stem on those that were already sprouted whenever the flood treatment occurred to see if that would cause any stress. And the treatment groups were broken up between either complete ambience over the entire period, experiment period, or complete saturation for all of the growing season. Or I tried to increase the ambient period between 2, 3, and 4 months, starting from the beginning of the growing season. Or I tried to decrease the growing season by having flooding over the top of the seeds, so not allowing them to sprout for 1, 2, or 3 months going into the growing season. So that shortened their amount of time that they would have to grow before November. And then I also tried pulses to imagine if we did releases of water from the dam, if we could do that, would that affect what species were most productive and able to survive? My hypotheses were that swamp species will decrease, their emergence will decrease with longer durations of ambient soil conditions, so drier soil conditions, and that low bottomland hardwood species, their emergence will decrease with longer durations of saturated soil. In terms of mortality, I assumed that there would be more mortality across all species with longer durations of ambient conditions if we got some drought conditions and not much precipitation over the experiment period. In terms of the final height of the seedling, I believe that the swamp species, based on past literature, would be tallest in the saturated treatments, and that the low bottomland hardwood species would be tallest in the ambient or drier soils. So, looking at emergence, this is the results here. We're not going to dig into this entire figure. We're just going to highlight the main results. You'll see that there are some similarities among treatments, not a lot of differences, but we did have some significant observations within. So if we focus on overcup oak, looking at the ambient versus saturated, so complete ambience over the experiment period versus complete saturated soil over the experiment period, we noticed that overcup oak emergence was significantly reduced in saturated soils. That's a good sign for us as restoration ecologists who are trying to add water to, say, the spider's cut system to try and maintain and boost the swamp forest type. We also noticed that extended floods reduced the emergence of ogeechee, pop ash, and water hickory. So if flooding goes into the growing season, extends into the growing season, this tends to have a species-specific negative response for ogeechee, pop ash, and water hickory. A certain dynamic for us to keep track of and look at the past hydrologic record to think about how that might be affecting these species. As we look at the rate of emergence, this is where we notice probably our most significant dynamics between swamp versus low bottomland hardwood species. So you have your swamp species, lowest elevation species on the left column here, and your low bottomland hardwood competitors on the right column there. And there's some significant trends to note. Look at that within the first 3 weeks of the experiment, almost 100% of all successful seeds sprouted for the swamp species. Whereas in your bottomland competitors, it was a much more gradual sprouting process. And so think about the disadvantages and advantages of these two different strategies. If you sprout all of your seeds early in the season, you're vulnerable to a longer time period of potential stresses that could occur. Whereas if you gradually sprout your seed lot, you might lose some during an early season stress, but you have others that are going to sprout later on throughout the growing season. So you have a better chance of having some successful individuals within this season rather than potentially losing all of your seeds to a stressor earlier on. So to understand why they have these strategies, we have to look at the seed physiology. So seed carbohydrates affect the emergence strategy and their resilience in that first growing season. Water hickory and overcup oak are very heavy-seeded, have very heavy-seeded nuts. So a lot of stored carbohydrates in that seed. That allows them a lot of resilience to stressors and an ability to re-sprout a shoot if they lose that initial shoot. So say a heat event or a flood event kills that first shoot that you see there, they have enough stored carbohydrates to then send up another after that event is over. Now with swamp species, on the right, they're very light seeded. So not many stored carbohydrates. If they lose that first stem, that first shoot that they put out, that is it. That seedling is not resprouting again. They haven't built a large enough root system with stored carbohydrates to send up another shoot. And so that kind of explains their regenerative strategy. If you have a light seed, you want to sprout them all and have the longest growing season possible to build carbohydrates in your root system and have a better chance at attaining resilience. Because if you only have a short growing season, then your chance of building resilience is much shorter. And so the low bottomland hardwoods have an advantage in this realm. And so our changes in hydrology within this system might be advantaging these low bottomland hardwoods. In terms of cumulative emergence, we noticed the most significant thing that we noticed in the top right-hand quarter is that even the rate of emergence for overcup oak was reduced in a saturated soil environment with that yellow lagging line there. So again, that's good news for us who are trying to add water to the system to inhibit those species from dominating in swamps. In terms of mortality, young swamp species were affected by early season scorching high temperatures. That happened to be the early season event that affected them. It could also happen in terms of predation or flooding events, but they were not able to recover from that. So they had a higher level of mortality in the ambient environment due to those higher temperatures. Now later on in the growing season, we had some low temperatures that we didn't get much precipitation, so we went into a drought period that caused some mortality in all species, mostly low bottomland hardwood species that weren't able to respond from that. But as far as the early season heat stress event, you see here that the bottomland competitors were able to recover from that, whereas the swamp species were not. And that again goes back to their stored carbohydrates in the seed. In terms of final height, our main observations between ambient and saturated treatments was that the swamp species were tallest in the ambient treatments, which goes against past observations from the literature that said that they grew best in saturated soils. Your low bottomland hardwood species, their height was actually reduced in saturated soils, which again is a good sign for us trying to restore hydrology in these systems. You also, something to note with overcup oak is that they have faster initial height growth advantages in a shortened growing season. So they would put on within the first few weeks about 14 inches in height compared to your swamp species that put on height much more gradually. So in a shortened growing season, overcup oak has a bit of an advantage there. So our conclusions are that maintaining saturated soil is very important. It reduces oak establishment and reduces low bottomland hard growth in general. So that's good news for us doing restoration work in these systems. Early season stressors, however, are detrimental to light-seeded swamp species. That's one of our most significant observations from this study. So how are we applying these conclusions? Going back to our original questions, what is driving species shifts? Is it increased hydrologic variability? Can swamp species not advance in a drier floodplain? Well, we've observed that drought is not a likely driver of increased swamp mortality. We can begin now to model the timing and duration of conditions that drop soil moisture below 5% to potentially cause mortality in these systems and see if that is a significant contributor to species composition. But it is more likely that early season stressors are the driver of swamp mortality and decreases in densities within the Apalachicola. So, are early season flood pulses increasing swamp mortality? We are currently modeling early season flows that could potentially cause swamp mortality in unsuccessful regeneration years for these species. There's a current effort to develop what we're calling biological and ecological metrics within the Apalachicola. We want to find out if there's any similarity in requirements for vegetation, mussels, fish, oysters within the system, what levels of flow allow them to be successful. And I've been focusing on the vegetation and the swamp species, so tupelo and ash. And I want to determine what hydrologic requirements do they have for a successful regeneration year. We take modeled river flows that look at the past hydrologic record, and we found a way to incorporate current water demands, current climate variables, how that would have affected the past hydrologic record, which allows us to now look at how tupelo and ash would have been affected over the hydrologic record. We determine the inundation flow threshold for floodplain swamps. And then we figure out what determines a germination event. So when the flow first drops below the threshold for greater than 7 days, based on my studies, if this happens between March and July, we know that there is a germination event that occurs. So all of the swamp species are going to germinate the majority of their seeds within 3 weeks after that event. And now a mortality event is likely to occur when flow exceeds that threshold within 21 days. So these seedlings then become flooded, and it remains up for 15 days. Based on past literature from Crochelle and King, we know that a majority of mortality is likely to happen with these species under these conditions. So we know if an unsuccessful regeneration year is likely to happen based on these metrics. This year, looking at the hydrologic record for this year, the hydrograph, it looked like we were looking at an unsuccessful regeneration year because you can see with the swamp inundation threshold line that flows dropped below for 7 days, and so we likely had a germination event, and then flows came right back up to flood those seedlings that likely sprouted. And this is just to give you an example of what a potentially unsuccessful regeneration year would look on the hydrograph. So once we determine these things, we look at the dam water control manual and try to determine if the current procedure increases mortality events, and can the procedure adapt to climate, water demand, and ecological needs. Finishing up here with our final questions. Can low bottomland hardwood species not advance in flooded swamps? We know that establishment of overcup oak is limited in saturated soils, but they are less affected by flood once they become established. So once they've had a long enough growing season, we know that flooding in the winter season and pulses are unlikely to affect these species. So the key is to keep them from getting established originally, all right? So affecting their emergence, so keeping saturated soils in these systems to not allow these competitors to move in. The drier floodplain is likely driving the advance of low bottomland hardwood species. And so our additional questions moving forward is, are drier conditions increasing ground vegetation competition in swamps like you see in this background picture? Is that potentially shading out or competing with tree seedlings too much? Do we have too much of an open canopy that's allowing this dynamic? We need to dig into this. Can restored hydrology restore ecosystem function within reasonable timescales? So over many decades now, we've had these competitors move in, establish, become full-fledged trees in the canopy. Restoring hydrology is not likely to kill those trees. So how long will it take for them eventually to be outcompeted and allow those swamp species to again regain dominance in the canopy. It is likely that we'll need to do low bottomland hardwood removals in swamps in order to increase the timeline of ecological restoration here. So I'll finish with that. I hope you enjoyed that. That's the basis of my dissertation work, and we're continuing on with all these questions going forward. So I'll take any questions you might have now.
Thank you, John. That was great. If you want to come off mute, you should be able to unmute yourself and ask a question, or you can raise your hand, or you can type it in the question panel. You may have stunned everybody with all of your information, and they may not have any questions. So.
I know that was a lot.
No, I think it was a lot of really great information. It's a lot to think about. I know I teach a couple of classes that deal with the floodplain, and all of it's subtle. You know, there's things that it's not always straightforward, as your experiments have shown.
Right. Yeah, and we're just making incremental advances here in our understanding.
Yeah, but that's true with all science, I think.
Oh yeah, for sure.
I see somebody. Let's see. Just looking at the hands raised. Let's see if anybody. Okay, Candy, did you have a question? You should be able to unmute yourself. Oh, let me unmute you here. I don't know why, but did you?
Here I am.
Oh, good.
How does the Apalachicola River compare to like a bigger floodplain like the Mississippi and other rivers that, you know, empty into the Gulf? I mean,
In terms of forest dynamics?
Yes.
Yes. So no, I'm glad you asked that, because the Apalachicola, our problem here is very specific. So talking about it, we're really kind of making the low bottomland hardwood species out to look like the culprit or the bad competitors here. That's just specific to this system where they're moving into the swamps. They are a native species, but we would like to maintain those swamp habitats here because we believe that those species provide nutrients to the system that are important to the Bay Estuary downstream. Now in the Mississippi River Alluvial Valley, where we've levied majority of the lower part of the river, we've cut off a lot of the low bottomland hardwood species, the floodplain that once supported low bottomland hardwood species, like overcup oak, like water hickory. These species are still important to wildlife in different floodplains and provide other services. And so it's important for me to Oh, I'm sorry. I didn't realize I got muted there. But what I was trying to say is that species like overcup oak and water hickory are important species in other systems like the Mississippi River, where they've been, where we've lost them to drying habitats or drying floodplains that have been disconnected by levees, or where we've cleared a bottomland hardwood forest for agriculture. We're now trying to restore some of those areas. And so in the Apalachicola, it's just a specific problem where those species happen to be moving into the swamps, and we're trying to restore the swamps.
That answer your question, Candy?
Yes, thank you.
Great. Beth, do you have your hand raised? You should be unmuted. You're self-muted, so just.
Okay.
Great.
Well, hi, I'm Beth. I live in Apalachicola, and I'm a wildlife biologist.
Nice.
And I have a master's. And I was thinking more about the personal in conducting your dissertation research. Like, how many years or seasons did you go through all these different experiments? And was it kind of stressful that a lot of them did not provide the evidence you were looking for in your hypothesis?
Oh yeah, for sure. I mean, I guess that's science and research in a nutshell. It doesn't always work out the way you necessarily expect it to. But so I tried to do those studies as quickly as I could. So I was doing a lot of field research as well and monitoring out in the Apalachicola itself. But that monitoring, in order to see trends out in the floodplain, it's going to take a long time. We need to see, trends over decades to really get an idea of what's going on currently. And so I wanted to do what I could in a controlled environment over a short time period. And so that's why I wanted to do these seedling studies. So I started, I think, in 2022, and then I took those residual seedlings in 2023 to do the secondary experiments. So yeah, it was a couple years, and so I had to work really quickly to make sure I could churn out the dissertation in time. But these were really important questions to ask, and I had other studies going on where the other question was, what about shade tolerance? Tupelo, the swamp species, is listed as heavily shade intolerant. So the question is, are these competitors advancing into the canopy and shading out those Tupelo seedlings? But the reality is that a lot of tolerance ratings for tree species in the literature are not necessarily based on experiment or empirical study. It's just based off of observation. So, we notice these species prefer these wetter sites. So we'll say that they are very flood tolerant, but we've never really tested it. So I wanted to test that with Tupelo, and I've actually observed through experimentation that Tupelo is highly shade tolerant. It actually grew pretty darn well in up to 60 and 90% shade. So yeah, lots of questions to ask. It doesn't always get you right to the answer, but that's just part of the process.
Thank you.
Great. I don't see any more questions. John, we thank you so much for being with us. It was a very enlightening talk, and we really appreciate your time. I just wanted to invite everybody. We don't have a Sci-Cafe in August, but we do have one on September 26th. We will be the contractor who is working on the Tate's Hell restoration. As many of you know, one of the early restore projects was restoration in Tate's Hell Forest to put some of the roads and forest roads back to their natural habitat, and that will also provide more flow into the Apalachicola River. So we'll be talking about that on September 26th. And John, we wish you all the luck in your new position, and hope to hear more about your ongoing studies.
Awesome. Thank you so much for having me, and thanks for listening today.
Yeah, thanks everybody for joining us. Okay, whoop. We appreciate it. And
awesome.
I'll send you a link to the recording too.
Okay, sounds great.
Okay.
Well, I guess I'm gonna pop off. Have a good rest of the day.
You too.
All right.